Stop scrolling. 2025 just rewrote the universe. The universe has always been a source of wonder, a vast expanse that sparks our curiosity and drives us to explore. Every year brings us closer to understanding its secrets, but some years stand out as truly transformative. The year 2025 is shaping up to be one of those landmark periods in the history of space exploration. We've witnessed a cascade of discoveries that have stretched our imagination and, in some cases, completely rewritten our cosmic textbooks. From the dawn of time to our own solar system, 2025 has delivered one breathtaking revelation after another. It's a year that reminds us just how much is still out there, waiting to be found. What makes this year so special? It's the sheer breadth and depth of the breakthroughs. We aren't just talking about one or two isolated findings. We're seeing a convergence of new data from a host of incredible instruments. Mighty telescopes like the James Webb Space Telescope are peering deeper into the past than ever before. Daring robotic probes are venturing to uncharted territories, sending back views we've only dreamed of. At the same time, private companies have stepped onto the stage, proving that the final frontier is no longer the exclusive domain of government agencies. This powerful combination of technology, ambition and collaboration has created a perfect storm of discovery, fueling an unprecedented era of cosmic insight. In this special report, we're going to count down the 12 wildest, most fascinating space discoveries of 2025 so far. Think of it as a highlight reel of humanity's greatest scientific achievements from this year. We'll journey from the fiery explosions of the universe's first stars to the icy moons orbiting distant planets in our own galactic neighborhood. Each discovery on our list represents a significant leap forward in our quest for knowledge. These are not just minor updates or technical footnotes, they are game-changing moments that challenge our assumptions and open up entirely new fields of inquiry for scientists to explore for decades to come. The stories behind these discoveries are as compelling as the findings themselves. They are tales of human ingenuity, persistence, and the relentless desire to answer the biggest questions of all. Where did we come from? Are we alone? What is our place in the cosmos? The answers we've started to uncover in 2025 are more profound and surprising than anyone could have predicted. So, get ready to have your mind blown. We're about to embark on a journey through the most incredible cosmic revelations of the year, each one a testament to our species' unyielding drive to look up and wonder what's out there. To guide you through this extraordinary year, we've organized the top discoveries into a countdown format. We'll start with incredible breakthroughs and build our way up to the most mind-bending revelation of 2025. This structure will help us appreciate the scale and importance of each new finding. But this isn't just about listing facts. For each discovery, we're going to break down the complex science into clear, simple explanations. You don't need a PhD in astrophysics to follow along. Our goal is to make the universe accessible to everyone. These discoveries belong to all of us, the collective achievement of humanity. The heroes of our story are a diverse cast of characters. You'll hear a lot about the James Webb Space Telescope, a revolutionary observatory that continues to exceed all expectations by capturing light from the universe's infancy. We'll also follow intrepid space probes, like ESA's Solar Orbiter Probe 3. On the ground, observatories like LIGO are listening for the faint whispers of cosmic collisions. And we can't forget the bold new players in the commercial space sector who are making lunar landings and missions to Mars seem closer than ever. As we explore each item on our countdown, we won't just tell you what was discovered. We will focus on why it matters. How does finding an ancient supernova change our understanding of stellar evolution? What does the discovery of a new moon around Uranus tell us about the formation of our solar system? How does confirming one of Stephen Hawking's theories about black holes impact fundamental physics? We will connect the dots, showing you the bigger picture and exploring the potential impact these findings will have on our view of the universe and our future in it. Each breakthrough is a puzzle piece, and by the end, you'll see how they begin to form a new, more detailed image of reality. Promise yourself that you will stick with us through this journey. We promise to deliver a clear, compelling, and awe-inspiring tour of the cosmos as we now know it. We'll unravel the mysteries of ultra-bright galaxies, interstellar comets, newly imaged exoplanets. We'll celebrate major milestones in human spaceflight and marvel at the robotic precision that makes it all possible. By the conclusion of our countdown, you'll not only be up to date on the latest science, but you will also share in the excitement and wonder that drives exploration. The universe is speaking to us, and in 2025, we learn to listen in a whole new way. Table of Contents, Part 2. Act 1, The New View of the Early Universe. Section 1, Peering Back to Cosmic Dawn. Section 2, The Supernova That Shouldn't Look Familiar. Section 3, The Case of the Overly Bright Galaxies. Section 4, Seeing the Void in Three-Dimensional. For as long as we have looked at the night sky, we have been looking into the past. Light, the cosmic messenger, travels at a finite speed. So when we see a star that is 100 light-years away, we are seeing it as it was 100 years ago. This simple fact of physics transforms our most powerful telescopes into veritable time machines. No telescope has proven more effective than the James Webb Space Telescope. In 2025, Webb kept flexing its muscles, staring so far that it witnessed the universe during its infancy, the cosmic dawn, the era when the very first stars flickered on, ending the cosmic dark ages. Before Webb, views of this early period were blurry, like trying to read a distant sign without glasses. We had theories and educated guesses. We imagined them to be primitive, simple structures, the building blocks for grander, more complex galaxies like our own Milky Way. But Webb is a game-changer. Its giant gold-coated mirror and its sensitivity to infrared light capture the faint, stretched light from the first objects. It slices through obscuring dust and gas to reveal the universe's earliest moments. This year, Webb delivered a high-definition revelation that sent shockwaves through astronomy. The discoveries from 2025 are forcing us to discard old assumptions. It's like an archaeologist finding a fully functional smartphone in an ancient Roman villa. Webb's data shows a young universe far more advanced than predicted. The universe grew up fast. Structures were more complex, events more dramatic, and the cosmic landscape more organized. In this first act, we'll explore 3 key Webb discoveries reshaping our view. First, the explosive death of one of the universe's earliest stars. Second, a baffling population of galaxies too bright to exist under old theories. Third, Webb used the echo of a more recent explosion to map invisible structure in 3D. Together, these findings paint a wilder, more intricate picture of our cosmic origins, one that is more intricate and mysterious than we had ever dared to imagine. Our journey into the cosmic past begins with a bang. the biggest bang you can imagine, short of the Big Bang itself. In March of 2025, a network of telescopes on Earth detected a powerful flash of high-energy light from across the universe, a gamma-ray burst. These are the most luminous events known to occur, briefly outshining entire galaxies. This particular burst, catalogued as GRB 250314A, was special. Its light had travelled for over 13 billion years to reach us, meaning the event happened when the universe was only 730 million years old. That's just 5% of its current age. This was a signal from the dawn of time, and astronomers knew they had to get a better look. This is where the James Webb Space Telescope came in. While the gamma-ray burst itself was fleeting, the afterglow of the explosion that caused it, a supernova, could linger. Webb turned its powerful eye to the coordinates of the burst, hoping to catch the fading light from a collapsing massive star. And it succeeded. As Andrew Levin of Radboud University put it, only Webb could directly show that this light is from a supernova. This was it, the earliest, most distant supernova ever directly confirmed. It was a monumental achievement, a direct observation of the death of one of the universe's first generation of giant stars. Scientists were ecstatic, ready to analyze this pristine relic from a bygone era. But when the data came in, the excitement turned to bewilderment. The team analyzed the light from the supernova, breaking it down into its chemical fingerprints to understand its composition and characteristics. They expected to see something alien, something befitting a star born from the simple hydrogen-helium. Our models predicted that these first stellar explosions would be fundamentally different from the ones we see today, which occur in stars enriched with heavy elements forged over billions of years of cosmic recycling. The universe's first stars were like simple recipes with only 2 ingredients. Modern stars are complex dishes with a whole pantry of elements. Incredibly, this ancient supernova looked normal. It was almost indistinguishable from supernovae that have occurred much closer to us in space and time. This was a complete shock. How could a star from the dawn of the universe die in the same way as a modern one? It suggests that the processes of stellar death are perhaps more universal than we thought, or that the early universe became chemically enriched with heavy elements much, much faster than our theories allow. It's a profound puzzle. Finding this familiar-looking explosion so early in cosmic history challenges our entire timeline of how the universe evolved, how it built up its chemical complexity, and how the stars that produce those chemicals live and die. Section 3. The Case of the Overly Bright Galaxies. As if a confusing supernova wasn't enough, Webb delivered another major shock to our understanding of the early cosmos. Astronomers at the University of Missouri were using the telescope to conduct a deep survey, essentially taking a long exposure photograph of a patch of sky to see what faint, distant objects they could find. When they analyzed the images, they found something they couldn't explain. Sprinkled across the field of view were around 300 objects that were shining with an intensity that defied all logic. According to our current understanding of galaxy formation, these objects, which appeared to be some of the earliest galaxies ever formed, were far too bright for their age. Our models of early galaxy formation are based on a bottom-up approach. We believe that after the Big Bang, small clumps of dark matter slowly pulled in gas, which then ignited to form the first stars and small dwarf galaxies. Over billions of years, these smaller galaxies would gradually merge and collide, building up into the larger, brighter and more structured galaxies we see today, like Andromeda or our Milky Way. This is a slow, methodical process. According to this theory, galaxies in the first billion years of the universe's existence should be relatively small, dim, and somewhat chaotic. They simply haven't had enough time to grow into brilliant, cosmic metropolises. But these 300 objects fly in the face of that theory. They are blazing with the light of billions of stars, suggesting they are either incredibly massive, are forming stars at a shockingly furious rate, or both. They look more like teenage galaxies than infant ones. This discovery forces us to ask some fundamental questions. Did galaxies form much faster than we thought? Was the process not a slow, bottom-up construction, but a rapid top-down collapse of massive gas clouds? Or is there some other, completely unknown physical process at play that made these early galaxies shine so brightly? Perhaps the first generation of stars were far more massive and luminous than our theories predict. Whatever the answer, these ultra-bright galaxies present a major challenge to our standard cosmological model. It's not a matter of tweaking a few parameters in a simulation. This could require a complete overhaul of our theories about how cosmic structures came to be. It suggests that the conditions in the early universe were far more conducive to rapid, large-scale galaxy formation than we ever imagined. The universe, it seems, was in a hurry to get the lights on. These 300 cosmic enigmas are now prime targets for follow-up observations, as scientists race to understand what makes them so special and what they can tell us about our own galaxy's ancient origins. Section 4. Seeing the Void in 3D. The universe is not just stars and galaxies, it's also the seemingly empty space in between them. This space isn't truly empty, of course. It's filled with a tenuous, clumpy mixture of gas and dust, known as the interstellar medium, or ISM. This is the raw material from which new stars and planets are born. Understanding its structure is crucial to understanding the life cycle of galaxies. For decades, we've studied the ISM, but we've mostly seen it as a flat, two-dimensional projection on the sky. We could see clouds and filaments, but we couldn't really grasp their true shape or how they were arranged in space. It was like trying to understand a forest by looking at a single photograph, instead of walking through it. In 2025, Webb changed that with our first true three-dimensional map of interstellar space. It used a clever trick involving a stellar explosion. Webb pointed at Cassiopeia A, the remnant of a supernova whose light first reached Earth about 350 years ago. As that light travels outward, it acts like a cosmic flashbulb, illuminating dust and gas it passes through. That creates a light echo, where different parts of the clouds light up as the flash sweeps across them. By observing those echoes over time, astronomers can map dust location across the sky and critically in depth. The results were absolutely stunning. Webb revealed fine dust details that resembled wood grain. The ISM wasn't random clumps, but vast, thin, sheet-like structures.
Researcher Josh Peak, we did not know that the interstellar medium had structures on that small of a scale. The
team mapped cosmic sheets on scales of about 400 astronomical units. That's 400 times the distance from Earth to the Sun. Finding such delicate organization in chaotic space surprised everyone. This discovery is transforming our view of the galactic ecosystem. These sheets likely play a critical role in star formation. They can channel gas, trigger the collapse of dense clumps, and influence the overall evolution of the galaxy. Understanding this invisible architecture builds more accurate star formation models. It's like discovering the hidden network of roots and fungal filaments beneath a forest floor. Thanks to Webb and a long-dead star, we are no longer just looking at the universe. We're beginning to see its true, underlying structure in glorious three-dimensional. Section 1. A new way to see a planet. For centuries, planets in other star systems, exoplanets, were purely theoretical. Then, for decades, we could only detect them indirectly, by observing the subtle wobble of a star as a planet tugged on it, or the tiny dip in a star's light as a planet passed in front. These methods were revolutionary, revealing thousands of worlds, but they left us wanting more. We wanted to see them. Direct imaging, actually taking a picture of an exoplanet, is the holy grail of planet hunting. It is incredibly difficult, like trying to spot a firefly next to a brilliant searchlight from miles away. The star's overwhelming glare usually washes out the faint light reflected by any orbiting planets. In 2025, the James Webb Space Telescope may have achieved this monumental feat in a groundbreaking new way. Astronomers aimed the telescope at a young star named TWA7, and using its advanced instruments, they managed to capture what appears to be the first direct image of a planet discovered by Webb. This wasn't just any planet, it was a world with a mass similar to Saturn, a gas giant in a wide orbit around its star. While other telescopes had directly imaged planets before, they were typically much, much larger than Jupiter. This potential discovery would represent the lightest planet ever seen using this direct imaging technique, pushing the boundaries of what is possible. This achievement, if confirmed, marks a major milestone for Webb and for astronomy as a whole. It demonstrates the telescope's unprecedented capability to not just find planets, but to directly observe them. This is a game-changer because direct imaging offers a wealth of information that indirect methods cannot provide. By capturing the planet's light directly, scientists can begin to analyze its atmosphere, looking for the chemical signatures of gases like methane, water, or even oxygen. This opens the door to studying the composition and weather of alien worlds in stunning detail, moving us from simply cataloguing planets to truly characterizing them and assessing their potential for hosting life. The discovery around TWA7 is more than just a technical triumph. It is the dawn of a new era in exoplanet exploration. For the first time, we have a tool powerful enough to take family portraits of other solar systems, revealing not just the massive, easy-to-spot giants, but also smaller worlds closer in size to those in our own cosmic neighborhood. Each new world imaged directly is another piece of the puzzle, helping us understand the diversity of planetary systems across the galaxy. It brings us one step closer to answering that profound question. Are there other Earths out there? With Webb's new vision, we are finally equipped to find out. Section 2. The Ghost Moon of Uranus. Our solar system is a place we think we know well. We have sent probes to every planet, mapped their surfaces, studied their moons. But even in our own backyard, there are still secrets waiting to be found. In February 2025, the James Webb Space Telescope reminded us of that. It made an unexpected discovery in the cold, distant realm of the ice giants. While observing the faint, dusty rings of Uranus, astronomers spotted something new, a tiny, previously unknown moon, provisionally named S2025U1. This little world had managed to elude discovery for decades, a ghost in the Uranian system. How did this moon stay hidden for so long? The only spacecraft to ever visit Uranus up close was Voyager 2. It flew by nearly 40 years ago, in 1986. During that brief encounter, Voyager 2 discovered 11 new moons. But S2025U1 is so small and faint it was missed in the probe's data. It took the power and sensitivity of Webb's NIR cam to finally spot it. This brings Uranus's known moons to 29. It expands the planet's satellite family and adds a new character to its complex tilted rings and moons system. Finding a new moon is exciting, but this discovery matters for what it tells us about formation and evolution of ice giants. The orbits and compositions of small moons like S2025U1 can hold clues about the system's violent past. They may be remnants of larger bodies shattered by collisions, or captured objects that strayed too close to Uranus's gravity. By studying this moon's orbit and properties, scientists can refine their models. Webb's discovery highlights its transformative power for planetary science in our own solar system. Famous for peering into the distant universe, Webb is also unmatched at exploring our neighbours. Its sharp vision sees faint objects and subtle details previously invisible, effectively bringing a new, more powerful probe to every outer planet system. The discovery of S2025U1 makes you wonder, what other hidden moons, faint rings, planetary features, are still out there waiting for Webb's gaze to bring them into the light? Section 3. A visitor from another star. Most of the objects in our solar system were born here. Planets, asteroids, comets, but every now and then we get a visitor from afar. An object that was born in another planetary system, travelling for millions of years through the dark void of interstellar space that happens to wander through our neighbourhood. In 2025, we got a close look at just such a traveller. The object, designated 3I Atlas, was the third known interstellar object ever detected. It was a comet, an icy snowball from another star, and its passage presented an unprecedented scientific opportunity. As 3I Atlas made its closest approach to the Sun, a fleet of spacecraft turned their attention towards it. American probes, Chinese probes, European probes. This coordinated international effort was a testament to how important these objects are. Each one is a free sample from another solar system, a priceless chance to study the building blocks of planets from a completely different part of the galaxy. Analysing its composition and trajectory could tell us if other planetary systems are built from the same stuff as ours, or if the ingredients for planets vary wildly from star to star. One of the most remarkable achievements of this observation campaign involved ESA's Trace Gas Orbiter, a spacecraft currently in orbit around Mars. By observing the comet from its unique vantage point, the orbiter's team was able to help predict the comet's path with incredible precision. This was a historic moment. For the first time ever, positional data from a spacecraft at another planet was officially accepted by the Minor Planet Center, the global body responsible for tracking such objects. It was a beautiful demonstration of how our network of robotic explorers can work together, transforming the solar system into a single, cohesive observatory for watching the skies. On November 19th, NASA unveiled a treasure trove of data and images from their observations of 3I Atlas. The information gathered by our robotic emissaries gave us our most detailed look yet at an object from beyond our solar system. The data revealed fascinating details about its journey, its incredible age, and its chemical makeup. These interstellar travellers are like messages in a bottle, thrown into the cosmic ocean from a distant shore. And with 3I Atlas, we finally had the tools to read the message inside, offering us a tantalizing glimpse into the nature of worlds orbiting a star far, far away. Section 4. The chemistry of an alien comet. When scientists analyzed data from 3I Atlas, one thing immediately stood out: its unusual chemistry. As the interstellar comet neared the Sun, its surface ice heated and turned directly into gas, a process called sublimation. That produced a glowing atmosphere, a coma around the comet's nucleus. By studying the light from the coma, astronomers read what gases were being released. They found the usual suspects: water vapor, carbon monoxide. But they also found something in surprisingly high abundance: carbon dioxide. This unusually high CO2 content was a major clue. In our solar system, CO2 versus other ices depends on where a comet formed. Comets from colder, distant regions usually have more CO. Comets from slightly warmer, closer regions tend to have more CO2. The chemistry of 3I Atlas suggests it formed in a different region of its home system than our comets did. That gives us a chemical fingerprint of its birthplace. This single data point has profound implications. It implies the snow line, the freeze distance from a star, can vary a lot between systems. And that variation changes how planets are built. The composition of icy planetesimals, the building blocks of giant planets and water deliverers, is not universal. 3I Atlas's CO2-rich nature suggests each star may have a unique planet formation recipe. By studying interstellar visitors, we're doing galactic-scale comparative planetology. We're no longer limited to just our solar system. Oumuamua, Borisov, 3I Atlas. Each adds a new dot on the graph, helping us see what's common and what's rare in planet-forming disks. This alien comet didn't just put on a show, it gave a crucial piece of the puzzle about how planets form. Our Sun is the heart of our solar system. It's the engine that drives our climate. It's the source of all our energy. It's the star we know best. Yet, for all our study, huge parts of it have remained a complete mystery, specifically its poles. From our vantage on Earth and most spacecraft, we look at the Sun from its equator. We've never had a good direct view of its north and south poles. Imagine trying to understand Earth by only looking at the equator. You'd miss the ice caps, you'd miss the auroras, you'd miss crucial aspects of global weather. The same is true for the Sun. In 2025, that all changed. The ESA solar orbiter performed a daring maneuver. It completed its fourth flyby of Venus. It used Venus's gravity to tilt its orbit. It climbed out of the flat plane of the planets. The slingshot pushed its inclination to 17 degrees. That gave it a high-latitude perspective. For the first time, a spacecraft could look down on the Sun's poles. In March, it began capturing the first direct images and videos of the Sun's south pole. That region had been hidden from our sight. The data was released to the public on June 11th. The images were breathtaking. These views are more than pretty pictures. The Sun's poles are key to understanding its 11-year activity cycle. That cycle drives solar flares. That cycle drives coronal mass ejections. Those eruptions can disrupt satellites and power grids on Earth. The Sun's magnetic field is thought to be generated by a deep dynamo. The poles concentrate the magnetic field lines like a giant bar magnet. Seeing the poles lets scientists watch how the magnetic field evolves and how it eventually flips, the event that marks solar maximum. It's like finally seeing the engine's inner workings. With these images, solar physicists can finally test their theories. They can study coronal holes at the poles. Coronal holes are the source of the fast solar wind. They can study plasma flows on the Sun's surface, and how those flows feed the magnetic dynamo. The solar orbiter has opened a new window onto our star. This perspective will deepen our understanding of stars and improve space weather prediction. Sometimes the biggest discoveries aren't about what you see, but, how you see it. To study the Sun's faint outer atmosphere, the corona, astronomers need to block out the blinding light from the Sun's main disk. This is what happens naturally during a total solar eclipse, when the Moon passes in front of the Sun. To create this effect artificially, telescopes use a device called a coronagraph, a small disk inside the telescope that blocks the starlight. But this method has its limits. Light still diffracts or bends around the edge of the internal disk, creating a glare that obscures the inner corona, the region scientists want to see. The European Space Agency had a radical idea. What if you could create a virtual telescope 150 meters long? What if you put the blocking disk, the occulter, on its own spacecraft? This is the ProBA3 concept. 2 satellites, one with a telescope, one with an occulter, flying in extremely precise formation. They maintain 150 meters apart with a precision of just a few millimeters. An astonishing feat of engineering, like 2 fighter jets in perfect tandem, one casting a perfect shadow from a football field away. In 2025, ProBA3 proved the concept could work. The mission achieved and maintained precise formation flying, a technological breakthrough. With the occulter far ahead of the telescope, the Sun's light is blocked far more effectively, dramatically reducing diffraction and glare. In June, the mission sent back its first coronagraph images, the clearest views of the inner corona ever obtained, revealing a hotbed of activity, where solar eruptions are born and the solar wind is accelerated to supersonic speeds. This demonstration is a game-changer for space science. It opens whole new mission designs. Imagine pairs of telescopes flying together to create interferometers with baselines of hundreds of meters to image distant exoplanets in stunning detail. Or imagine a star shade and telescope flying in formation directly blocking a star's light, letting us see faint, rocky planets. ProBA3 didn't just give us a new solar view. It gave us a toolbox for future observatories. For decades, landing on the Moon was something only superpowers could do. The missions were incredibly expensive and complex, but in recent years, private companies started entering the fray. In 2025, commercial space took a giant leap forward. NASA's CLPS program partners with private companies to deliver science to the Moon. The mission, Firefly Aerospace's Blue Ghost Mission 1. On March 2, 2025, Blue Ghost touched down softly on the lunar surface. A successful landing is a monumental achievement many have failed to accomplish. But the mission didn't stop there. Over its time on the Moon, the lander exceeded expectations. Designed to carry a suite of scientific instruments for NASA and for other customers. It performed flawlessly, a data-generating powerhouse transmitting over 110 gigabytes back to Earth. That surpassed any previous commercial lunar mission, setting a new standard. The quality matched the quantity. The lander sent back stunning, high-definition lunar images. Most valuable, the lunar horizon glow, seen at sunrise and at sunset, likely from electrostatically levitated dust. Blue Ghost gave the best measurements of that to date. It also captured an Earth eclipse from the Moon, giving data on Earth's atmosphere and the faint solar corona, complementing missions like ProBA3. Blue Ghost validates the commercial partnership model. Private industry can deliver high-value science at a fraction of the cost of government missions. This opens the Moon to wider scientific investigation. Instead of one or two big missions per decade, imagine a steady stream of smaller landers to many locations. This changes planetary science. More risk, more innovation, and a faster pace of discovery on our nearest celestial neighbour. Section 4. The breakthroughs of 2025. Solar Orbiter's polar views, Proba 3's formation flying, Blue Ghost's data deluge. Together they signal a fundamental shift in planetary science. We are moving away from the old one-size-fits-all battleship-class missions. Instead, an era of diverse, specialized, technologically nimble exploration. Faster, more creative scientific responses. Era defined by precision, partnership, new perspectives. Proba 3's precision engineering is central. Multiple spacecraft flying millimeter-perfect formations. Formation flying unlocks new observatories. Not just for the Sun. Formation telescopes with effective mirrors hundreds of meters across. Sharp enough to map exoplanet weather. Or to see accretion disks around black holes. Robotic precision makes space part of the instrument. A revolutionary next generation of great observatories. Commercial missions like Blue Ghost are democratizing access. Lower cost and higher launch frequency mean we can take more risks. Send probes to more diverse, challenging places. Test unproven tech on small missions before flagship use. Today's small lander test instruments for tomorrow's flagship. That cycle accelerates discovery and builds resilience. These advances change our tools and our philosophy. The solar system becomes a single, interconnected laboratory. A Mars orbiter can help track an interstellar comet. A commercial moon lander can complement a solar observatory. Spacecraft become networked robotic senses. Collaborative, tech-driven exploration is the future, already here in 2025. Table of Contents. Part 5, Act 4. Extreme Events and Human Space Milestones. Section 1, Echoes of a Cosmic Collision. Section 2, Hawking's Final Victory. Section 3, The Next Giant Leap. Section 4, A Quarter Century in Orbit. Section 1, Out in the silent darkness of the cosmos, events of unimaginable violence unfold. Stars collapse, galaxies collide. Black holes spiral towards each other in a deadly dance. The dance ends with a cataclysmic merger. These events shake the fabric of space-time. They send out ripples called gravitational waves. For most of history, we were deaf to these symphonies. But now, incredibly sensitive instruments on Earth let us listen in. LIGO acts like a giant ear, waiting to hear the faint chirps of distant mergers. They are the ultimate cosmic alarms. On January 14th, 2025, the alarms went off. Twin LIGO detectors in the US and the Virgo Observatory in Italy registered a clear, powerful signal. It was the sound of two black holes, many times the mass of our Sun. They swirled faster and faster, then merged into one. The event happened in a distant galaxy, hundreds of millions of light-years away. Its gravitational waves travelled across the universe at light speed to tell us the story. Each LIGO detection gives us a new laboratory to test physics under extreme conditions. Conditions we could never replicate on Earth. This merger was special. The signal was strong enough for scientists to extract huge amounts of detail about the two black holes just before collision, and the single larger black hole left behind. By analysing the waveform, the signal shape, they could calculate the masses, the spins, and even the sizes of the objects. This wasn't routine. It was a golden opportunity to test a profound prediction about black holes, a prediction made nearly 50 years ago by Stephen Hawking. The universe provided the experiment, and LIGO recorded the results. The story is one of patience and precision, a testament to the human drive to understand fundamental laws. Black holes are where gravity and quantum mechanics break down. They are the frontier of modern physics. Every gravitational wave is a clue from that frontier. The January 14th merger wasn't just noise, it was a message. When scientists decoded it, they found a resounding confirmation of a theory that had been impossible to prove until now. Section 2. In the early 1970s, Stephen Hawking was revolutionizing our understanding of black holes. He proposed a simple but powerful idea, the black hole area theorem. The theorem: a black hole's event horizon surface area can never get smaller. The event horizon. The point of no return. No matter what you do to a black hole, throw matter into it. Merge it with another black hole. The total surface area after a merger must be greater than or equal to the sum of the originals. It connected space-time geometry to thermodynamics. For half a century it stayed theoretical, untested. The black hole merger, recorded on January 14, 2025, provided the perfect test case. The LIGO team meticulously calculated the properties of the two initial black holes. Before they merged, their event horizons had a combined surface area of nearly 243,000 square kilometers. That's an immense area, roughly the size of the United Kingdom. Then they calculated the surface area of the single larger black hole that formed after the collision. The result was staggering. The new black hole had a surface area of roughly 400,000 square kilometers, nearly double the original combined area. It was a clear, unambiguous validation of Hawking's area law. The surface area had not decreased. It had, in fact, increased dramatically. This confirmation is a monumental achievement. It's a posthumous victory for one of the greatest scientific minds of our time. But it's more than just a tribute. The area law is a cornerstone of black hole thermodynamics that seeks to unite Einstein's theory of general relativity, quantum mechanics. Proving the law in a real merger gives physicists a much firmer foundation to build theories of quantum gravity. It tells us that we are on the right track in our quest to understand the universe at its most fundamental level. The result also deepens the mystery and beauty of these cosmic objects. The idea that the surface area of a black hole behaves like entropy, a measure of disorder which can only increase, is a profound link between gravity, thermodynamics, information theory. Why should a geometric property of space-time be governed by a law that also describes the shuffling of molecules in a gas? This 2025 discovery doesn't answer that question, but it confirms that the connection is real. It sharpens the puzzle and gives scientists a solid new data point as they work to unravel the deepest secrets of space, time, gravity itself. Section 3. The next giant leap. While some of our instruments were looking back to the dawn of time, others were focused on the future, humanity's future in space. And in 2025, no one was dreaming bigger than SpaceX. For years, Elon Musk has spoken of making humanity a multiplanetary species by establishing a self-sustaining city on Mars. This has often sounded more like science fiction than a concrete engineering plan. But in May of 2025, Musk presented his most detailed timeline yet. He announced a 50% chance of launching its first uncrewed Starship mission to the Red Planet by late 2026. This wasn't just wishful thinking. It was a plan based on the rapid progress of the Starship development program. The first flight, Musk explained, would be a cargo mission. It would carry supplies and equipment to test landing procedures and scout potential sites for a future base. Intriguingly, it would also carry a simulated crew, a team of Tesla-built humanoid robots named Optimus. These robots would be tasked with performing initial setup tasks on the Martian surface, acting as robotic pioneers before the first humans ever set foot there. The plan is for the first human crews to follow on the second landing, or the third landing, potentially within the decade. However, this ambitious timeline hinges on overcoming enormous technical hurdles. The single biggest challenge is not the launch or the landing, but what happens in between, on-orbit refueling. A Starship vehicle simply cannot carry enough propellant to get to Mars and back from a single launch. The mission architecture requires a fully fueled Starship to be waiting in Earth orbit, acting as a tanker. Another Starship, the one going to Mars, would launch and then rendezvous with this tanker to top up its fuel tanks before beginning its long interplanetary journey. This complex high-stakes orbital maneuver has never been attempted on this scale and is the critical technology that will make the Mars mission possible. The plan laid out in 2025 represents a pivotal moment. It marks the point where the Mars mission transitioned from a distant dream into a tangible engineering project with a proposed schedule. While the 50% chance for 2026 is admittedly a coin toss, the very fact that such a mission is being seriously planned and resourced by a private company is a paradigm shift in space exploration. It signals the dawn of a new space race. One not between nations, but driven by a commercial ambition to open up the solar system. Whether Starship makes it in 2026 or 2028, the journey to Mars has, in a very real sense, already begun. Section 4. A quarter century in orbit. While we dream of future outposts on other worlds, it's important to celebrate the human presence we've already sustained in space. In November 2025, humanity passed a truly historic milestone. 25 years of continuous human habitation aboard the International Space Station. Since the first crew, Expedition 1, floated through the hatch on November 2, 2000, the ISS has never been empty. For a quarter of a century, day and night, astronauts from around the world have lived and worked in low Earth orbit, creating a permanent human foothold off our planet. An unparalleled achievement of international cooperation and engineering endurance. The ISS is more than a place to live, it's a world-class laboratory. Over 25 years, it hosted more than 4,000 scientific experiments run by researchers from over 100 countries. In microgravity, astronauts have pushed the boundaries of science. They've studied how the human body adapts to long-duration spaceflight, knowledge critical for missions to Mars. They've grown protein crystals of purity, impossible on Earth, leading to new drug developments. They've studied combustion, they've studied fluid physics, they've studied materials science. To mark the anniversary, NASA highlighted 25 major breakthroughs from the station's research. Those breakthroughs show the ISS's lasting impact. New methods for water purification now used in remote communities on Earth. Deploying satellites that track global shipping and aid disaster response. Creating stronger metal alloys by studying solidification without gravity. The station is also a vital platform for Earth observation, offering a unique view of our changing climate. Observing deforestation. Monitoring the health of our oceans. The 25-year milestone is a moment for reflection. The ISS stands as a shining example of what humanity can achieve together, a beacon of peace and collaboration, even in tense times on Earth. Looking forward, new commercial space stations, ambitious missions to the Moon, ambitious missions to Mars. The ISS taught us how to live in space, how to work in space, and how to use space's unique environment to improve life on Earth. It is the first chapter in humanity's long story of becoming a spacefaring species. Section 1. A Universe Reimagined. As our countdown comes to a close, it is clear that 2025 was not just another year in space exploration. It was a turning point. The discoveries we have journeyed through have fundamentally altered our cosmic perspective, painting a new, more vibrant and more mysterious picture of the universe. The James Webb Space Telescope, our ultimate time machine, revealing a young universe far more advanced and chaotic than predicted. The discovery of a familiar-looking supernova at the dawn of time and a population of impossibly bright galaxies has forced us to literally go back to the drawing board. We have also ventured to worlds both near and far, expanding the frontiers of our knowledge in every direction. For the first time, we may have directly photographed a planet the size of Saturn, opening a new chapter in the search for other worlds and the characterization of their atmospheres. Closer to home, we found a new ghost moon hiding in the Uranian system, reminding us that our own cosmic backyard still holds secrets. And with the visit of the interstellar comet 3I Atlas, we captured and analyzed a messenger from another star system, giving us a priceless glimpse into the chemical diversity of planet formation across the galaxy. Each discovery has been a new thread, weaving a more complex and fascinating cosmic tapestry. The year was also a triumph of human ingenuity and precision engineering. We watched as the solar orbiter gave us our first ever direct view of the Sun's south pole, a critical step in understanding the engine that drives our entire solar system. We marveled at the Proba 3 mission as it demonstrated a new paradigm of formation flying, a technique that will undoubtedly shape the great observatories of the future. The success of commercial partners like Firefly Aerospace on the lunar surface has flung the doors wide open for a new, faster and more agile era of planetary science. These technological leaps are the engines of discovery, the tools that turn imagination into observation. Finally, 2025 was a year of profound milestones. We celebrated 25 years of continuous human presence in space aboard the International Space Station, a testament to our endurance and our capacity for international collaboration. We saw the dream of Mars become a tangible engineering project, with SpaceX charting a course for the Red Planet. And in the silent depths of space, the collision of two black holes sent ripples through space-time that, when they reached us, provided a stunning confirmation of Stephen Hawking's theories, solidifying our understanding of the universe's most extreme objects. It has been a year where the past, present and future of exploration all converged in a brilliant flash of discovery. Section 2. The Journey Ahead. So, where do we go from here? The revelations of 2025 have not just provided answers, they have gifted us with a whole new set of deeper, more compelling questions. These discoveries have laid the groundwork for the next decade of exploration, setting the stage for even more profound insights to come. The journey is far from over. It feels like it has just begun. The universe has shown us that it is more complex, more surprising, more wonderful. The drive to understand it has never been stronger. The momentum from this landmark year will carry us forward into a new golden age of astronomy and spaceflight. Looking ahead, there are several key things to watch. The James Webb Space Telescope will continue its deep stare into cosmic history. Astronomers will hunt for more ultra-bright galaxies. Astronomers will hunt for ancient supernovae to determine if they are anomalies or the new rule. Follow-up observations of the planet candidate around TWA7 will be crucial to confirm its status. Then begin detailed analysis of its atmosphere. Every new direct image will add another family portrait to our growing album of other solar systems. Bringing us closer to the day we image a world that looks something like our own. On the human front, all eyes will be on SpaceX and Starship. We will watch critical tests of on-orbit refueling. That capability unlocks the path to Mars. The success of the commercial lunar program will spur more missions, landers, rovers, perhaps the first elements of a permanent lunar outpost. The International Space Station will remain a vital science hub. New commercial stations will begin to take shape. The universe reveals itself to us, but only if we have the courage to look. The discoveries of 2025 remind us we are living in an extraordinary time. A privileged moment where the secrets of the cosmos are within reach. Keep looking up. Keep asking questions. Support the science and the explorers. The next great discovery could be just around the corner, waiting in the faint light of a distant star or in the data from a daring robotic probe. The journey ahead is bright, and the cosmos is waiting.